Okay, hello and welcome. This is SFU Math 232. It's Brenda. This is our special Halloween edition. Happy Halloween. This is the lecture on composition and invertibility of linear transformations. That is section 6.4. Okay, I think this lecture will be a little bit shorter than the last. That may or may not be good news. Okay, all right. So suppose we have a transformation, T1, and it maps Rn to Rk. And then we have a second transformation which matches Rk to Rm. So first thing to notice is this and this have to match. Those two things those both have to be Rk. So the thing what we can do is put these two transformations together via the composition operator, and we will denote that this way: T2 composed with T1, or we will say T2 of T1 of x. And that is the idea there is that we take a vector, we first operate on it by T1, then we take the output of that and operate on it again, that output by T2. So for example, we could rotate the vector by 30 degrees and then we could reflect it over the x-axis. And we would compose those two operations and form one transformation matrix. We can form one transformation matrix then that does both of those operations at the same time with one matrix multiplication. Okay, so that's what transformation composition of a transformation. This is very similar, same as a function composition. Okay, we do have to be careful that the dimensions are right. When you've seen single variable functions, you haven't not had to worry about the dimensions. Okay, so let's get theorem out of the way here. That is, if we have one transformation taking us from Rn to Rk, and then we have the second transformation taking us from Rk to Rm, and both T1 and T2 are linear, then the composition of the two of them will also be linear. So the proof of this is quite straightforward, and really it serves as a good reminder of what does it mean to be linear. So I'll just write that out as a reminder. Linear means, by the definition of linear, t of x plus y equals t of x plus t of y. And also t of kx equals k t of x. Okay, so those are the two things that you need for something to be linear. So what we're going to do is just go through the composition of these two transformations and show that they satisfy both, that the composed transformation satisfies both these requirements, and then that will have, the proof will conclude that T2 of T1 of x is also linear. So we're going to do it this way. We're taking a look at T2 of T1 of the vector x plus y. That is T2 of T1 of x plus y. And that is equal to T2 of T1 of x plus T2 of x. Sorry, not plus T2. Plus T1 of y. T1 of y. That is based on the linearity of T1, because T1 and T2 are both linear. Then that is equal to T2 of T1 of x plus T2 of T1 of y. That is based on the linearity of T2. And then that we can rewrite in this manner: T2 of T1 of x plus T2 of T1 of y. And so that the first condition for the linearity of the composition is satisfied. Then we take a look at the second condition. So that's the additivity condition that was just satisfied. And we take a look at the second condition. Perhaps stop the video, do it yourself, and then check back. Okay, so that looks like this. let's get it correct. We're going to compose T2 with T1 like that, T2, and this is going to be T1 of Kx like that, and then that will be T2 of K, T1 of X. That's by the linearity of T1, and then that's equal to K times T2 of T1 of X. That's by the linearity of T2, and that is equal to K times, and we are done. It's the homogeneity, um, uh, this one here, has now also been satisfied. So we first showed this condition was satisfied, then we showed the second condition satisfied, so we are done. The composition is linear. Okay, suppose again we have two linear transformations. We immediately check that that dimension matches, and T1 and T2 are linear transformations. That means they can be represented in a matrix. So, and then we have the matrix size here. So the matrix for the first, because T1 is a transformation from Rn to Rk, the transformation matrix, this guy, when we represent that transformation in a matrix, it has to be a K by N matrix. And similarly for the second, so we're calling this guy here A, and then similarly the size requirement for the T2 transformation, it's going to be that matrix we're calling B, and that is going to have to be M by K. Okay, so then we can figure out what the standard matrix must be for the composition. So we have this. Like that. We are simply required to multiply these two things here. So this is the transformation encoded by matrix B, composed with the transformation encoded by matrix A, is the transformation encoded by BA. Okay, note the order. Okay, so the order has to be right. And we have to do it in the right order, and it's important to do it in the right order because we recall that matrix multiplication is not commutative. So that tells you right now that composition is not commutative. Okay, there's a statement of what we just looked at there, sitting there as a theorem with a few notes below here. The standard, well, we know this is standard linear transformation T. We can denote it this way. That is the matrix that encodes that that linear transformation. So we can then write it like this if we want. T of x equals the matrix that encodes T multiplied by x, and then we have this notation here as well. Okay, let's take some examples. If we have a rotation matrix, or we have a linear transformation that rotates about the origin by an angle omega, and then we're going to compose two of those, what happens? So we have two of these. So the matrix that encodes the rotation by angle beta is this guy here, cos beta minus sine beta, cos beta. The matrix that encodes the rotation by alpha is cosine alpha minus sine alpha, cos alpha, like that. So now I'm going to find the matrix that encodes their composition, and that is going to be the product of these two matrices, cos beta minus sine beta, cos beta, multiplied by cos alpha minus sine alpha, cos alpha. Okay, I do that multiplication. It's a little bit painful, I admit, but let's see what happens. I get here cos beta cos alpha minus sine beta sine alpha. And this one is sine. So this is 2 by 2 matrix multiplication. You can check me, make sure I don't make a mistake here. It's going to be pretty easy to write something wrong. Okay, let's get the next two entries here. Minus cos beta sine alpha minus sine beta cos alpha minus sine alpha sine beta plus cos alpha cos beta. There it is. Okay, so then you will recall the trig identities. I'll have to move that back in a sec. We'll recall the trig identities for cos x plus y and sine x plus y. We are going to use those trig identities right here to write this like this. Cosine alpha plus beta minus sine of alpha plus beta, sine of alpha plus beta, and cosine of alpha plus beta. Okay, and then what do you see? Then this actually is actually the rotation about the origin by an angle alpha plus beta. Okay, this totally makes sense. I mean, imagine I have some vector here, and I'll just draw what the composition looks like. I have that vector there. First thing I do is I do T1, which is a rotation here by alpha. So this is my original vector v. Then this is T of v, a rotation by alpha. Then I apply to that, I apply another rotation, and I go here by beta, like that. And so this becomes, this is actually, let's be careful here, we've called this T alpha. Now I'm going to apply T beta to T alpha of v. So that's this guy right here, T beta of T alpha of v. Call it v, not x, of v. There it is. Okay, and as you can see, that the net effect of first rotating by alpha, then rotating by beta, is to rotate here by alpha plus beta. So this rotation here is alpha plus beta. Okay, that's not, I mean, that's what you would think if you thought about it geometrically without multiplying the two standard matrices for these operations. But now we can see if we multiply these two standard matrices, use a trig identity to simplify, then we see that we do get the matrix which does exactly what we expect, rotated by the sum of the two angles. Okay, so if were we to want to do those two rotations at the same time, then we would use this composition matrix here. Okay, what happens if we reflect? Okay, let us take a look at that. We're going to reflect about a line through the origin, angle omega to the x-axis, and then we're going to compose two of those and see what happens. So here we're going to have, for this reflection operator, we're going to have T of alpha be cos 2 alpha. So this is a standard matrix for reflection about a line that is at angle alpha to the x-axis. Okay, and then we've got beta will look like this. One that we rotate by, reflect over that line, beta to the x-axis. Okay, I'm going to then multiply these two guys together. And what will I get? I will get a huge thing here. I'm going to put the first one here and leave the other 3 for you to fill in. This is going to be cos 2 beta cos 2 alpha plus sine 2 beta sine 2 alpha. So of course there's an entry here, an entry here, and an entry here. And do you do that multiplication and write out what those are? And then we're going to use the trig identities for sine x minus y and cosine of x minus y. So we're going to employ those 2 trig identities, and then we will observe that this thing is this thing here, cosine of 2 beta minus 2 alpha, sine of 2 beta minus 2 alpha, and minus sine of 2 beta minus 2 alpha, and cosine of 2 beta minus 2 alpha. Okay, now we ask ourselves, what is this? If I just took a look at this matrix and said geometrically, what is that? Okay, so first thing we're going to do is notice where the negative signs are. That's very helpful. So you notice the negative sign here, and then notice the negative sign here. That does not match up. And then looking up above, we see on a rotation, the negative sign is there. So I'm looking at this and I'm realizing if I were to notice that I had like alpha, 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 alpha here, and I would just think that I have the same thing here, 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 and here, and then I have cos minus sine, sine, cos, I have a rotation matrix. This is a rotation matrix. So that rotation this is a rotation by 2 beta minus alpha. Okay, so if I choose to do these 2 reflections and compose them, that is the same as doing a rotation by this angle here. So draw a little picture for yourself. Draw a vector reflected over some line, and then draw another line, and then reflect that output that you just got over that line, and draw it carefully enough so that you can see that that is the equivalent of doing this rotation. Okay. That's what we can say about them. So they can be represented geometrically. Oh, and what can we say about the compositions? We've got the composition, this one, t of beta of t of alpha of x, and then we have here t of alpha and t of beta of x. Okay, in the first case, in the case where we have a composition of 2 rotations, these things are going to be equal. But in the case where we have the 2 reflections, they are not going to be equal, because when I reverse this, it's not going to be the same angle. Okay, so like I think we just said earlier, matrix multiplication is not commutative. I mean, sometimes it could be, special cases it can be, but in general it is not commutative. So in general, these things will not be equal. All right. What about if we want to take an inverse of a one-to-one transformation? So we suppose that we have a one-to-one transformation. It has to be one-to-one, otherwise the concept of an inverse is not going to be making sense. And what does this mean? It means that if we take a vector w in the range of t, so an output, then there exists a unique vector x such that t of x equals w, and that x is called the preimage of w. That's what it means for it to be one-to-one. So then if we have that case there, the inverse, which we're going to denote in the usual way of denoting an inverse, is a transformation with the range of t, is transformation with, yes, with the range of t, and let's just see range Rn. Let me just put a little slight question mark there. I'll come back. I'm coming back to that. So what it means is that if we take the inverse transform of W, we get back to X, if and only if T of X is W. So let's just write this here. So what does this mean? If I compose T with T inverse of W, then what I am saying, what this will be is W. But what I'm saying is I would do this in two steps. First, I would say the inverse transformation on W will get me to X, and then the transformation on X will get me to W. That's that W right there. Similarly, if I do it the other way, if I take the transformation of X, I get to W, and then I take the inverse transformation of W, I will get back to X. So this here is X. Okay. Let us just assume that this will clear up this problem here. T is a one-to-one linear transformation. Then so is the inverse transformation. So T is one-to-one. That's the key point. So let us just draw a picture of this to sort of see what this looks like. We have here, over here we have the domain of T, just some numbers, it doesn't matter, like that. And over here we have some codomain. Like that. And then we have a transformation. And so I'm going to set up a one-to-one transformation here. That is going to be T of 1 is equal to A. T of 2 is equal to B. T of 3 is equal to F. And T of 4 is equal to D. Okay, it's not an onto transformation because these guys, nobody goes there. Okay, so what is the range of T? The range of T is equal to A, B, D, and F. Okay, the codomain is equal to A, B, C, D, E, and F. Okay, the domain of T is 1, 2, 3, and 4. Okay, now our inverse transformation is going to go back. So T to the minus 1 of A is going to be 1. Maybe I'm going to rewrite that. I'm just going to do it in a different color. So to see that is clearly going the other direction. So I'm going to note here, I got T to the minus 1 of A is equal to 1. So that is the guy going back this way like that. And then I've got that T to the minus 1 of B is 2. And that is this guy going back here like that. Okay, the other two are similar. Okay, so what do we have? We have that the domain of T to the minus 1 is equal to the range of T, and that is equal to here what I've got, sorry, I was thinking about something here. That is going to be A, B, D, and F. Yeah, so I'm pausing momentarily as I'm thinking, oh, but I could apply my inverse transformation here to those as well. So I'm going to ditch this little thing here and instead state that what I want to say instead is that the range of T to the minus 1, that's going to be 1, 2, 3, and 4, and then that is equal to the domain of t. That's more solid. There we go. Sorry about that. All right. Okay. The final thing to say here is that we sometimes will use this word here, invertible, then instead of this word here. So one-to-one linear operators are invertible. So we might call a one-to-one linear operator an invertible linear operator. Okay, so and we have a statement here that is that if we have a one-to-one linear operator, then the standard matrix is the inverse of the standard matrix. So that's this here. This is our inverse transform. And then what the inverse, if we have the transformation T encoded with matrix A, then the transformation T to the minus 1 is encoded with matrix A to the minus 1. Okay? So we get the inverse of a transformation by taking the inverse of the matrix. Let's see an example. Okay, we want to find the inverse of rotation about the origin in R2. So we're going to do this sort of by visual picture, and then also actually compute it and make sure that we see that this is working exactly how we would expect. Okay, so that is the rotation matrix. R theta is cos theta minus sine theta, cos theta. Okay, now let's think about what's happening here. And that is this. We take a vector, v, there it is, and we rotate it by an angle theta. We get over here. It's the same length. So we rotate it over to here. Let's call it W. Okay, I think it's fairly obvious that if we want to go back, get back to where we started from, to undo this, we would go like that, and we would rotate by an angle minus theta. Okay, so I would expect that the inverse of this matrix would be this. We'll show that it is. So I would expect, based on my sort of geometric analysis there, that r theta to the minus 1 would be r of minus theta, which would be this guy here, cosine of minus theta, sine of minus theta, is sine of minus theta, and cosine of minus theta. And that is cos theta sine minus sine theta minus sine theta cos theta. This last step here is based on the fact that the cosine function is even and the sine function is odd. Okay, so I've got that there. Let's see. Hang on, something might have gone wrong. There should have been a minus sign right here. Yeah, hang on, I'm substituting in here minus theta. Sorry, I made a mistake. I'm just going to make sure I don't still have a mistake. I'm substituting in minus theta into each one of these. Yeah, I just dropped that negative sign. So now I'm here minus sine of minus theta, so this thing should be a plus right there. Plus. Okay, so I now claim that this thing here is the inverse matrix to this guy here. Let's see if that's true. I'm going to take them and multiply them together. I would expect to get I. Let's try it out. So I'm going to take r theta and multiply by r theta to the minus 1. That is going to look like this. Cos theta minus sine theta cos theta. And I'm going to multiply that by cos theta sine theta minus sine theta cos theta. And what happens when I do that, folks? I get cos squared theta plus sine squared theta. And then I get cosine minus sine cos. Good. Same thing here. And then here I get sine squared theta plus cos squared theta. And that is equal to this, 1, 0, 0, 1. That's the identity matrix. So I have that this product right here is the identity matrix. That means, of course, that these two things are most definitely inverses. Okay, so, but you can, if so, for example, if you're being asked to find the inverse of this matrix, really, if you're thinking about it geometrically, and you're like, oh, that just means you have to rotate back, you could quite quickly write this down without going through the whole procedure for finding an inverse. Okay, let us think about what happens in the case of a reflection. What happens if I reflect about a line? Okay, let us draw a picture. Now I have some line here. It is at angle phi to the x-axis, and I take some vector, and I wrote, I'll just take, like when I take a vector here, and then I'm going to reflect it over here, like that. So I reflect that across the line. So this is, yeah, let's just call this guy V, and then this is W. So I'm gonna V is the W is a reflection of V, and then I'm gonna ask, how do I get back? I'm saying I just reflect it back over the same line. So if I reflect over a line, I get a new vector, and then I take that vector and I reflect back over the line. I get back to where I started from. So I claim then from that, thinking about it this way, that the inverse is the same as the original operation. So I'm going to write here what the reflection matrix looks like. The standard form of the reflection matrix looks like this. Okay, and then I would claim, based on my geometric analysis, that the same exact matrix is also the inverse. Matrix is itself as an inverse. Okay, now what can I notice here? Well, one thing I could notice is that we talked about earlier, is that this matrix here is an orthogonal matrix. That means that the inverse is the transpose. So I'm now going to just take a quick look and see, is this true? I've computed the inverse. So now thinking about it geometrically, now I'm thinking about computing the inverse by saying, you know what, in this case, because this is an orthogonal matrix, the inverse is the transpose. And let me just write out what the transpose is. So I'm going to take this row and make it the column, this column. And then I'm going to take this row and make it this column. Sorry, it's not cos, it's minus cos 2 phi. Minus cos 2 phi. Okay, there we have it, folks. We can see that transpose is, which we know is going to be the inverse, and that is in fact what I wrote down, thinking about the fact that if you reflect over a line and then want to get back to where you start, you should reflect yourself back over that same line. Okay, let us do another example, possibly in a slightly different way. Let's find what is the inverse for horizontal shear. So here's the matrix for horizontal shear. Looks like that. Okay, let's find the inverse. Just as a way of recalling one method we've seen of computing inverses, let us find the inverse that way, because it's super easy to do. We have to do one row operation, R1 minus KR2. And that gets us this guy here, 1, 0, 0, 1. And then over here I get 1 minus K 0, 1. So I now know what the inverse of that horizontal shear is. It is this guy here, 1 minus k 0, 1. Okay, so I mean this again I think kind of makes sense if you take something like that and you shear it in the x direction like that by k, and then what you need to do to recoup is take it and shear it in this direction by minus k, and you get back here. Okay, so that's what that's telling us, and we should be able to multiply a times a to the minus 1 and get I, show that they are inverses. Okay, that is all for section 6.4. A little bit of a shorter lecture, and well, as usual, I'll be back with the next lecture shortly. See you later.